First time I came to Thailand was back in 1997. Actually, the research we did involved all Southeast Asia, and my boss back then, he had my ambition to expand my research beyond the project we worked in before, and that included to do more work also in Thailand. More or less on the topic I'm working on, and also on using satellites to study the Earth, which can be sea level rise, earthquake area. Of course, if the climate change or sea level rise is going to make problem for the beaches, for example, or some cities like Bangkok, then that will create stress for the people living there. So in some way, I hope that our work, or also my colleagues, will contribute to preserve the smile. So the Thai people can smile also when they walk onto the beach, and keep on doing that for hopefully many generations to come. Not only for my own interest, but also for the benefit of other people. This kind of work I've been doing. So when I came to Thailand, people are always nice. They ask you how you're doing. It seems genuine. It doesn't seem that they're just polite to you to expect something back from you. And that I really appreciate a lot. Thailand, the people seem to be more nice, always smiling, and very respectful also. So I really enjoyed that. Yeah, anywhere I go, I think Thai people always are friendly. So yeah, so it feels to me relaxed to be at home. Sawadee ผมชูวิมผมเป็นคนไทยขอโทษนะครับผมเป็นคนเบลเยียมทำงานที่เนเธอร์แลนด์ที่ Delft University of Technology.
Okay. So, yeah, good afternoon, everybody. As you hear, I can speak some Thai, but it will not be good enough to to give you all the technical details. So I will do it in English. I'll try to talk slow. So if it should be my presentation coming. Okay. First of all, also me, I've been more than 25 years in Thailand. So I also knew the previous king and the queen. I mean, and I really admire them, and of course we also want to pay respect with her passing away, and yeah, keep her in our memory. So today what I'm talking about is basically my contribution, and my contribution comes from the GPS side. Nowadays we call it GNSS, Global Navigation Satellite System. That's because GPS was of course the first system from the Americans, but nowadays we also have Galileo, the European system, GLONASS, the Russian one, Baidu, the Chinese one, and there's even some couple more systems. Most of the work I have done, of course, is with GPS, because GPS was already available back in the 1990s. And in this work, in this project, I use the GNSS mostly to look at vertical land motion, so what the land is doing at a certain location, going up or going down. Apart from that, the land can also, over a bigger area, deform. That's mostly related to tectonic processes going on. Far away, actually, most of them from Thailand, apart from the Chiang Mai area, but even the activity which you can see, actually I don't know if it will work, no, it won't work with my pointer. From Indonesia, Sumatra, you can feel, and also the earthquake in Myanmar, you can feel, although there is no direct big earthquake, well, it depends how big you want to, danger for the Bangkok region, but you can feel it. And then this vertical land motion, which I will illustrate you, if you combine that with the absolute sea level, so the sea is going up due to the climate change, Then we talk about the relative sea level rise, and that, of course, is most important um, for coastal regions, because if the sea is going up and the land is going up, that would be nice, but that almost never happens. And the land is going down due to human processes, mostly related to water pumping. Then, of course, you get a much bigger effect what the sea is doing with respect to your land, which is going down. So this is the work. I've not done it alone. What I present today is collaboration, you see, and also Captain Samart has been very useful, and also COSTAT for allowing us to and facilitating our work here inside Thailand for already many years. And Mark will also present later on, and another colleague I think is helping us a lot is Simon Williams from the UK, and that's also related to a new technique using GNSS to directly measure the seawater level. So GNSS as a tide gauge, which I will show you, which is quite new and it seems to work very well. We tested it in Phuket, which I will show you, and I think in the future it can be used also to monitor even better the sea level changes, not only daily, but also over a longer period of time. Okay. So the contents, I will briefly talk. Well, I read already a little bit about the relative sea level change, a little bit about the projections for the future, which are not done by me, but there's a global group doing for that. A little bit on our own research activities, because we also have our own stations in Thailand, 4 of them. Then the importance, again, I explain the title of this GNSS in relative sea level change studies, because that was one aim of to see the impact of relative sea level, where also, of course, groundwater pumping scenarios would predict the land subsidence in the future, and then we could combine that with absolute sea level rise in the future, and then we could get a more accurate prediction what it would mean for the coastal regions. Then I will tell you this new technique, GNSS reflections, or GNSIR. It's actually not complicated to do yourself. Very briefly, I have to talk a little bit still about the tectonics, because it has also a small contribution in the vertical deformation of Thailand. Mostly, of course, the closer you go to Sumatra, so the most effect we will see in Phuket, which is the closest to Sumatra, and then we still see in Bangkok, but there the effect already is scaled down. Then, if you present something or a new technique, you always have to ensure that you have more than one result or more than one technique to back up your scientific results, especially if you want to convince bigger audience or policymakers. So that's why the Phuket, we really have a very nice case where we can use all these techniques independently, estimate the same relative sea level rise and compare to see if it matches. And then, of course, we apply, we plan to apply also for the coastal regions in Bangkok. I think this project, that's not completely worked out, but we hope to continue. So I'll show you some results. Then I will show you a little bit about the Myanmar earthquake. It's not too much related to this project, because there were no vertical motions. However, it could have still a small effect. For example, if you have sand layer and water pumping, and then a big earthquake happens, it can mix everything and can cause some local deformation or vertical. I think there's one highway you see also which had subsidence after the earthquake. That was because the sand was already not stable below, but that's probably related to groundwater level change. So that's a little bit, but it just shows you again how powerful this GNSS also can be. And then about the relative sea level rise for the Bangkok area. And I will actually end with the result we did in a project together with colleagues also from Chulalongkorn University. I think more than 10 years ago, we already looked at it. Nowadays, we add the groundwater pumping, and of course our estimates on absolute sea level rise and land subsidence are getting better, more refined, but the basic technique already, we already looked at that more than 10 years ago. All right, so, and then to come back to the question about the temple, I will answer that one. So this is, I took this picture myself when I was one of the many times flying, I think towards Bangkok, I think that was that time. And then you see, of course, the coastal area, Samut Prakan area. You see the Chao Phraya River, and you see this whole area, you know, this coastal region area. And of course, that's the area which is going to be most affected because it's the closest to the sea. Now, if we show you another temple, should maybe look a little familiar. This is Wat Khun Samutrawat temple, and that one we visited actually a long time ago in the first project, and also with Femke we've been there. And actually this temple is very nice to illustrate the impact of relative sea level rise. And for an area quite close to Bangkok, or actually Bangkok province actually extends also some area close to the coastal region. So nowadays we call it the Greater Bangkok area. But yeah, there you can really see. And when we went to visit there, the people have this little, it's not a museum, I think it's in somebody's home, and you can go there, where they put a lot of picture on the impact for them of this, well, in the beginning, what the reason was. But you see three scenes there, and on the left, I think it was in the 1960s. The middle one, I think, yeah, you can see the tailleur, but it's not so clear. I think it was 1992. I think the last one is 2009. And then the red dot you see is always the temple. You can see in the 1960s the temple was quite a distance away from the sea, from the coastal area. And you can see in 1992 it was at the coastal area. In 2009 it was already far behind the coastal region or the low and high tide. But because the people want to preserve, they built the wall and they elevated parts of it so they could preserve the temple. But it actually showed a real impact of what could happen also to Bangkok, although the time scale will be probably different. But you see, if nothing happens, if nothing is done to prevent either the absolute sea level change, the sea from the climate change, or locally due to land subsidence related to groundwater levels lowering, then at some point you will have to build elevated ways. Well, for yes, you already have, because the ground level at some point starts flooding slowly, and at some point it will become, if you do nothing, and then the water will not go away, but it's a very gradual process, you know. So sometimes people ask us, so when Bangkok sinking will happen? Well, it's already happening for many, many years, but it's going very slowly. So, and it's never too late to do anything about it, but I will show you more. So this temple really shows you this effect of relative sea level rise. A combination of absolute sea level rise due to climate change. We have this problem everywhere around the globe. And then, of course, locally you can have land subsidence. So the land going down. And the combined effect, that's this relative sea level rise we're talking about. To illustrate you a little bit more, this a bit older results. This is again a map, and you see already there that the area is, of course, not too high above the sea. The Bangkok Plain has a very low slope, so you can go 50, 100 kilometers land inwards, and then I think you only go up 1, 2, 3 meters, you know, so it's very slowly going up. So that means, of course, that if the sea goes up a lot, the impact on the land will be much bigger. For example, in Phuket, you have a bedrock and you have a quite steep slope. So if the water go up there, it will still cause coastal erosion, but it's not going to go inwards, land inwards a lot. On the right, you see all the results we did in the past. Today, Mark, our expert on satellite altimetry, will present you updated results. But that's the absolute sea level rise in millimeter per year. You see 3 to 4 millimeter per year in the Gulf of Thailand. Then if we look at data from tide gauges we got in that, it's the same publication back, you see normally if there's no change in sea level, it should be a flat line, like you see the green, the purple, and the blue one. But you see explicitly the red and the black with red, which is corresponding to those two tide gauges you see on the left panel. You see that there's a very big increase, you know, even more than 1 meter. I think it changes and it starts in the late 1960s, and then you see there's a couple of big jumps. Disregard those. This is just an adjustment of the reference level they did, because it was going a bit out of scale. But you mostly see the trend. You see this. Yeah, quite increased, 1350 millimeter per year in between 1940 and 2003, and it mostly you see the big change starting in the early 60s. So this is quite severe, but most of the time the tide gauges, they are built on a concrete foundation, which is 10 meter, sometimes 20 meter deep. So that means that the tide gauge is going down with the land below the pillar, so below 10 meter or 20 meter. So the land on the surface can even have more land subsidence, because the tide gauge you don't just put on the sand, you put on a pillar, 5 meter, 10 meter. So probably the actual, what we also saw on the temple, land subsidence was higher on the surface. That one. It's the same with GPS. You measure what is happening below your foundation or the pillar you put your equipment on. Now, Thai people also have done some studies, publication 2010. Also here you can see, for the same area, you can clearly see how the coastline is retreating through the years, you know, in this area. So, it's again, you see a big change in coastline between 1974 and 1998. It's the same area where also the temple is located. Now that's the actual, what I show you a little bit is up to today. And also what we present today is what we measured till we stopped processing the data, which could be last year for this project, the end of last year. But of course, what's going on in the future? Because we can measure now what the land subsidence is. We can also measure what the absolute sea level rise is. But how does it change in the future? Does it change linearly, or does it change non-linearly? And then you have the IPCC. This is this big panel of scientists from many countries together, and they make this report and they make these estimations. You can see here, for the next 100 years, there is the blue one, that's the optimistic one, is showing an increase of less than half a meter. Well, if you took the errors into calculation, you could say around half a meter. But then if you look to the right, that's depending, of course, on the warming up of the Earth and how the emissions are, or the CO2 levels are lowered or not. You see that even it gets worse. You know, in that case, it's non-linear. And actually, we know already nowadays it's not the blue one is way too optimistic. The red one is much more representative. Now, if you look this for a couple of years more, and you can go to the year I think 2300. So that would be roughly 300 years, well, 275 years from now. Then you can see already that you can get global mean sea level changes in worst scenario of 5 meters, you know. So you know that most of Bangkok is only a few meters above sea level. So of course we will not be around here, and it's not our problem, and maybe not for our children or our grandchildren, but it will become a problem. And even the generation now will already notice the beginning of those effects. So you have these global models, which are very useful for us to predict. So if we have a result for Bangkok today, based on our own data, we can use this to extrapolate or get a more accurate prediction if what the situation would be if nothing is changing, or in the good or in the worst case scenario. What we also can improve ourselves is to get more accurate results, which is in red, on the vertical land motion, so by using our own data, because this is a global model. And also the sea level here, it's a global model, but you can do your own regional analysis, and it will still be a little bit different, because not everywhere on Earth the sea level is going up with the same amount millimeter per year. There's actually a couple of regions even where it can go down. But yeah, the global climate change is, the overall effect is of course, sea level rise going on. So the techniques, the one on top, that's the one mine. Well, not mine, the one I'm using, and then GNSS, plus this new one using the GNSS as a tide gauge, which has to do with reflections of the radio signals from the GNSS satellites on the sea surface, and then they enter the antenna. Actually, we call this data normally multipath. It's the data we don't want to use because it's not telling us anything about the real position of the antenna. But some scientists, I think 10, 15 years ago, I think they started in the US, they thought like multipath data to estimate also the sea level. If we know the satellite signal is reflecting on the ocean and then entering the antenna, we can also measure the sea level height by that. And I think in the last 10 years, this technique has matured and it's become very useful. The other three techniques, my colleagues will talk to you about that. Mark will talk about satellite altimetry, a little bit more about tide gauges. You see actually from the tide gauges on the left bottom, this is historical from more than 100 years. You can also see there very clearly that, especially in the last part, we are not linear anymore. So we are non-linear, so we are increasing more and more as we go in time. Insar Milan will also talk to you more about. So my own focus, apart from we are operating 4 stations ourselves, that's our contribution. We're also sharing this data in Thailand. We have similar stations in Malaysia, also Indonesia, also for research. But for me, it's important that over a very long period of time, we can estimate the daily position, both horizontal here I will not talk too much, but vertical, to see how the vertical position is changing through the years. And that, of course, we can then use to see what the impact would be on relative sea level rise. So yeah, the most areas I'm working myself on is Bangkok, Phuket, and Malaysia. We have done, and yeah, we get similar and comparable results also there. Then there's also a nice way nowadays, if you have different, I mentioned before, independent techniques, you can combine those to get the same results. So there is more than one scientific technique to measure, for example, relative sea level rise. A tide gauge is the direct way to do it, but there are now also 2 more other ways to do this. I will briefly show you, talk to you about that. So this is, if this could be Bangkok, you see there, just an illustration where you have the tide gauge measuring the relative sea level rise because it's connected to the land. So if the tide gauge is going down while the sea is going up, you get this much bigger effect. The satellite altimeter is actually an absolute measurement. It just measures the sea level over a period of time. So it will not be affected by land subsidence because it's an absolute measurement. Then we have the GPS station, which actually, in this case, we used to estimate the vertical land motion and land moving up or down. Although most of the time land is moving down nowadays. Apart from the Himalaya, where we have the coastal, the tectonic plates interacting and pushing the land up. But in coastal regions, it's mostly going down, and I think 99% due to groundwater levels changing. So the GPS, and then nowadays, if you put the GPS antenna near the sea, you can use the reflections from the satellites, and we call it GNSS, or I should name it ER, or GNSS reflections, which is then a direct measurement also of relative sea level rise, and should be 1-to-1 with the tide gauge, if you would have a tide gauge next to it. And then we have this very simple formula. I think Mark also will talk to you about it. Relative sea level rise comes from direct measurement from a tide gauge, but you can also obtain it from subtracting vertical land motion we get from the GNSS, from satellite altimetry, which gives you absolute sea level rise. Or another way now, since we have been doing it, I think, trying this out for like 5 years, using the GNSS ER. So using reflections from the satellites on the sea surface, and you track those over a period of time, and I will show you, you actually can see the daily tides in them quite clearly. So these are the techniques we have, which are the ones relevant for us. And of course, what Femke talked to you about before, also this groundwater is a new thing we have added, and that's also important also for prediction on different pumping scenarios for the future. Vertical land motion, I think I mentioned to you, you will get all a copy of the presentation. So just for you to know that I told you already that most of the time vertical land motion can happen because of tectonic plates interacting, and they move to each other, or they move away from each other. Then we have the human-induced land subsidence due to groundwater extraction, and seasonal changes, which can relate to the weather, atmospheric, oceanic, and hydrological loading. But these are seasonal or yearly signals, so they're not really a big concern, although you might want to know what the minimum and maximum is, for example, of the tides, so you can know what the maximum high tide will be. Same important for the wall around the Chao Phraya River. It has to be high enough during the high tides. But of course, if Bangkok is going down, you still have to know also this tide. But the seasonal changes are not, of course, it's more the trend over many years, which is important. Techniques I mentioned to you, I don't have to go to in detail. Now, I already told you before, you've seen also in Femke's presentation, GNSS, we have to say. And actually, I am using nowadays already GPS plus Galileo for the latest work we have done. And it gives you even a better result, mostly because it's more data. You have more measurements, more satellites, so you can get accurate. From you have to know that nowadays we can get a daily position. We do have to measure 24 hours. We can get already a sub-millimeter for the horizontal, and the vertical direction we can get a few millimeter accuracy. So depending on also how good the station, if it can see all the satellite, if there's no high buildings nearby blocking. But that's about the absolute accuracy we can get. Of course, if we measure that for many, many years, we should be able to see changes on this millimeter scale. For ourselves, I think the oldest station we have, well, the oldest station also Thailand has, is the base station at RTSD, at the Royal Thai Survey Department Survey School, near Sonam Loang. I think actually it's, near the Ratchathurn Boxing Stadium, actually it's located. This one, I think since 2005, we put the GPS there. So there we have 20 years now of data. And in the vertical, I will show you the result later. So this is the longest running core station in Thailand. And I'm happy also to see that in the past 10 years, also Thailand, different Department of Land, RTSD has started to put many more reference stations throughout Thailand, which can be used for mapping, but also can be used for scientific research. So that's nice to see. Need at least 5 years for the vertical to give you an accurate estimate. So what we are getting now about that period, because a lot of the stations were installed since 2019. So that's also interesting to look at in the future. Okay, relative sea level rise from TG. I already mentioned to you, so I don't want to. Mark will talk you a little bit more. Actually, you can see here, you can see already how long the cooperation, because this is actually Captain Samart when he was still at the Royal Thai Naval Academy. And it was me, I think 13 years ago. And you can see I still have much more hair, so you see how time goes by. But actually this is where we had the tide gauge in the back, and we put ourselves the GNSS there to directly measure the vertical land motion. This is not too far from the temple and the area. This is the naval base. And yeah, we measure land subsidence there. We see nowadays much less, but don't forget that, as I mentioned to you, this pier is on pillars. I think there are at least 10, probably 20 meters driven into the ground. So we can only measure what's happening below that, not what's in between. In between we can measure, like with INSAR, which Milan will show you. Okay, that's enough for that for you to take away. Then I mentioned to you already before, this new technique, or latest techniques, is making use of this reflections of the radio of the satellite signals bouncing off of the sea. So it's basically multipath. In the left side you can see a little bit the effect. So you have the direct, the blue one signal, that's the one we like to use for positioning, and then you have this indirect one which is bouncing from the sea and then entering the antenna a bit later. And then if you use this technique, you can see actually, you see the tidal. This is a month, so you see the different tidal related to the moon cycle. You see all those tides in there, which is exactly the same as the tide gauge would measure. Only the tide gauge you can tell to measure every minute or every 30 minutes. With GNSS reflection, it's a little bit different. And you need like 30 to 40 minutes of these reflections to estimate a water height. which you can correct, of course, for the tidal change in between that period. But it works very nice, and it's very complementary to a tide gauge. In the future, I think we can test this more. We did this in Phuket, but I think DMR also has two tide gauges already for some time, which have one I think is in Rayong, and they also have the GNSS, and we got there how good the reflections can match the tide gauge record. Okay, the plate motion. Again, I don't want to go too into detail. That you are aware that we are on a tectonic plate. Fortunately, this tectonic plate doesn't have big fault zones within Thailand, but the interaction of the different plates in India, Indian plate, Australian plate, and then the area we are on, we call Sundaland or Sunda, and that's the stable part of that is where Thailand, fortunately, and Malaysia is located upon. In the north of Thailand, of course, there is some interaction with this Himalaya syntaxis, and there you can have bigger earthquakes, but normally the Bangkok itself should not see big magnitude earthquakes because there's no big plate faults running. There are some faults running through Thailand, but they are not that big as the ones creating these 7, 8, and 9 magnitude earthquakes, which of course you're all aware of. So the plates are floating on the fluid interior. So a plate can never have a vertical motion because then it would move away from Earth, but it can deform near the boundaries. And the boundaries can be hundreds of kilometers thick. So actually the deformation from the Sumatra-Andaman subduction actually extends all the way even beyond Thailand. Only the effects become smaller and smaller as you move away. Because you see during the earthquake that then all the land is changing suddenly, which means there is a build-up for a long period because of this convergence of the two plates. Okay, so that's just the takeaway. Then there are 3 major phases. We call it, for these big earthquakes, we call it interseismic. That's between those big earthquakes, a period which can last 200, 300, 400 years. You have the co-seismic, that's the real earthquake happening, that's minutes, seconds to minutes, depending how big the magnitude is. And then you have this post-seismic phase, and that one can go on for decades, maybe 50, 70 from the last one. Nowadays, we are still in the post-seismic phase. So the whole land, Phuket, Bangkok also, but Bangkok much less, is still moving differently, horizontally at least, as it was before this earthquake. Just that you remember that we are post-seismic, okay? I don't want to put into detail. Then, yeah, we also did a real effect, a little study, but what would be the effect from the earthquake, because the earthquake, when it happened, also creates some changes in vertical land motion. And it was not too bad, and for the Bangkok area, the total effect we estimate back then would be only 10 centimeter change. But actually this is a cycle, which means that the Bangkok area, due to this tectonic process, will go down and up, but never more than this 10 centimeter, you know? So it will go down 10, and then in the next 200-300 years, it will go slowly up again. So it's just a big season. That's just the scientists want to get all the detail. You could say if the engineers build a wall, then they can add the 10 centimeter to be sure that they have this height enough, you know? But it's not a big issue. It's just to show you, yeah, we like to do everything in detail as much as you can. Then I want to quickly take you to Phuket. Why? Because there we actually did our study case. There was an there's a reference point there from a very early project we did in 1994. And actually RTSD was back then is doing the measurements, and the point is still being measured yearly as a reference point, although there are now many more core or continuously operating stations. But this means that we have this point for a long period of time, since 1994, and we also have GPS measurements from that. Then we have put 2 new points, one station near the shoreline, all on bedrock, so there is no land subsidence in Phuket, at least not where we put our station, because it's a rocky island, so you put the station directly on bedrock, meaning it's not going to go down due to changes in groundwater, you know, because we are in this case, we are not interested in that effect. So the one station is near the sea, as you can see, PMBC. So it should be able to measure the vertical land motion, but also should be able to measure as a tide gauge the changes of the sea level period of time. And the other one at Kota Noi is an existing tide gauge from the HGRTN, the Hydrographical Department from the Royal Thai Navy. We put also a GPS on the top of the roof. So also there we can both measure the vertical land motion and also use the reflections on the sea surface as a new technique to estimate the tidal changes, but we are more interested over a long period of time, 5, 10, 15 years, so we have to keep the station working to also estimate trends, trends, changes in relative sea level rise over time. So that's, and it's nice here because, and there's also actually a tide gauge from DMR nearby the PMBC, so we have 2 tide gauges, we have 2 GNSS, and we have a reference point for a long period of time, which we can measure at the same time or remeasure, so we can tie everything together and validate. Just to show you that, you have to, how we did it in 2017. So we have to select the location. First we want to put on the pier, but then we thought the pier over time is not going to be stable. You actually could see that the pier has been reconstructed, and at some point maybe they have to do, so we lose a point, so we decide to put at a little island. Of course you have to put a concrete pillar, make sure it connects. You need some equipment there. Mostly is a GNSS receiver, a battery, solar panel. And then you hope it will work for many years to come. And the station actually 2017, it is still running. We will go do an annual check, but it's running now for 8 years already. And I have stationed in Indonesia already running for 20 years. So we try to make them very strong, so they don't break down too quick, and we don't have to go too often because it of course costs time and money to do that. Now that result, what I told you, which makes our case stronger for the vertical land motion, is that you see here is the result for almost 27 years of recording the position of Phuket Island, because the station is representative for the whole island. And what the nice thing here is the 2 upper panels are actually the horizontal. I don't want to go into discussion about that one. And the bottom one is the vertical one. The vertical one is interesting. What you do see is that you see changes, especially because the 9.2 earthquake has changed there a lot, the horizontal motion. But what you can see is that those orange dots are the original point, which was measured independently by RTSD. And then we have the continuous stations, and since 2017, our own station, we have to connect them together because we didn't have one station operating for almost 27 years. But you see that the orange dots, they agree very well with the black ones, So also if you look at the bottom then, you see that before the earthquake, that was the blue area, before 2004, you see actually Phuket Island was moving slightly up because of this tectonic deformation. And after the earthquake, the land started to move down for a while. And even nowadays, it's non-linear. So in the beginning, you see a big fall of the land. But then through the years, you see it becomes less and less. You see the little seasonal variations, but those ones are not too not too important. Now, important for us is, if we talk about relative sea level rise, is these 3 techniques. You see on the right, you see panel A, satellite altimetry, an absolute measurement of the sea level, so not affected by what the land is doing. B is the tide gauge. And you see after the earthquake, suddenly there's a big increase of the sea level, but but you see through the years it starts to tail off. Now, if you look at the vertical motion of the land, you see exactly the opposite. You see that the island is going down quite rapid at the beginning, 1 centimeter per year, but then it's slowing. And of course, that means because the land is going down, the sea, or the effect, the relative sea level rise, is going up much more because it's this relative effect. And now we can see if we get the same result. Now, if you compare with the satellite altimetry, the absolute sea level rise, then through that period in time, we get a difference, I think, of 14 centimeter relative sea level rise. And only if you look at the tide gauge, we get 18. So it's not perfect. We are missing some centimeters. They come from part of it because of you have this very signal with much more tidal effects for the tide gauge. Also the tide gauge, sometimes the equipment is replaced, so we don't always sure if the vertical reference is exactly the same. If it's off or within 1 centimeter, for the tide gauge measurement, I think it's no problem, but for long term. But you do see that it's not perfect, but we do get an agreement. They both show this increase. Now, to show you that the new technique actually is quite useful, is that what you see in the middle is a tide gauge recording the sea level every day, I think every I don't know what the sampling rate is. I think we use here for this one hourly or daily points. That's the middle part. And then the upper part is actually reflections from the new technique. So using this signal bouncing from the sea surface and then entering the antenna. You see that the agreement is remarkably well, good. If you subtract both of them, you see that you are very close to the zero. There's some noise in there. There's a bit difference because each of the GNSS system can have a small bias, but they're still improving the software to remove that. So if you use GPS or Galileo, you see the same pattern, but maybe they are offset by 1-2 centimeters. Not a big issue, and I think it will improve. Now, the nice thing, of course, is if the tide gauge is broken for some reason, then the reflections can actually take over this registration, so you have much more continuity also in your data and less data gaps. And if there's a problem, yeah, you can figure out this if it's either the tide gauge, because you have more than one way to measure the sea level. Okay? And then you see if you combine all of them, even with the data gap here, because that means the GPS station had a problem, no data for a couple months. Yeah, then we can actually fill in the tide gauge, and we still can have a long time period observation. This was still a test. This is only 2017 to present, or end of last year. Yeah, I think this is a very promising technique to also observe relative sea level rise. And I think also in the future, more of the stations will be installed along coastal regions. So yeah, this one you saw from Femke. We don't have too many stations already for a long time period. If you look nowadays, I will show you in the result from the 7.8 earthquake. There are many more core stations nowadays. But if you go back many years, there was only one station from IGS since 2007, and then RTSD, the one they say the longest, 2005, SPKN near the Naval Dockyard. I think this one was since 2012. I think we installed that one there. So that's the time period we have available. Now, if you look at the vertical, which is on the right, you see that all of the stations in Bangkok, they show land subsidence going on. The rates are not that high. I think they are in between 3 to 5 millimeter per year nowadays, which seems little, but 5 millimeter per year is 1 centimeter in 2 years, and then you can add the effect after 50 years, still going to be half a meter. And as I mentioned before, this is the land subsidence below the depth of the pillar. Most of the pillars are 10 to 20 meters. So that means at the surface you can get much more subsidence, which can change over a period of time. Some of the water well, the groundwater wells are also higher than the 20 meter. So there you can see 3 centimeters. You will see Milan in the inside results. Actually, we can see different values. But yeah, this is what we can see. We can compare them a little bit with each other. So you see they look similar. But there are some variations as you move a couple of kilometers to a different location. Why? Because yeah, I think mostly the groundwater, the aquifers are different, and also it might be that the pillar is not the same depth. Actually, for all those stations, we should try to find out, which is not easy, the buildings they were built on, how deep the pillars are, to make even the results better in the future. Now, what we can also do is compare. This is the RTSD station. We can have, combining with older data from other stations, we can get this long time series, and we can see how it compares to Phuket. Well, I think you can see actually that it's the horizontal, it is scaled, the effect is less, but you see actually, in Phuket you see this bigger vertical land motion, but And you saw that before actually the land was going up, while before already Bangkok for a long period of time was land subsidence. The one in Phuket is related to tectonic, the one in Bangkok is related to groundwater extraction. Okay? The Thai government already put a policy in place to limit or restrict ground pumping. I think it has had a positive effect. Might not be perfect yet, but it might be. So what can we do? So what we planned to do was actually to come up in this project already with a more detailed result on the current situation of the relative sea level rise and the prediction for the future. And because everybody likes to know, or many times people ask me, when is Bangkok going to sink, you know, or when is going to happen? So already to not get that question again, I already put the answer there. But as we improve, refine our scientific results, we can make better predictions. The way it works is not that complicated. You can have a digital elevation model, or DEM, from the region. I think this one is an old example we made more than 10 years ago. This one only has 45-meter resolution, which means the digital elevation model jumps in blocks of 45 meters. Nowadays, there are much better satellites already are missions flown, and we have DEM nowadays, which is more accurate. That's the first one you have to do, get this DEM. You can connect it even in GIS and even put buildings there, so you can have even a better way to see what the impact of relative sea level rise would be. And of course, you always have to assume where is the zero level, because a digital elevation model was made maybe 5 or 10 years ago, but the sea level, or the mean sea level nowadays, is not exactly the same already as when the model was made. So we have to do some calibration, not a big issue. And then this case just assumed, very simple, 5 millimeter per year sea level rise, which is not too exaggerated, I think, and 5 millimeter per year land subsidence. Well, the 5 millimeter per year we have for sure. Bangkok, you see, the 3 stations show that. So that means the relative sea level rise is 1 centimeter per year. Now, what you will do now is that you're going to propagate through time. This is pure linear. Actually, we know now that it's not non-linear. Also from this IPCC prediction should be non-linear. We can extrapolate to the future. So what we're actually doing is taking our digital elevation model and adjusting the zero mean sea level for this sea level rise through the years. And then you will see that the areas, of course, will become flooded through time. This is very rough thing, just to show you how it works. And we did that in steps of 100 years. So don't panic, you know, but if you go, this is situation year 2000, then if we go, that would be 100 years from now, meaning if you don't do anything, also, blue, it means it's below sea level. That doesn't not mean it's flooded. If you, of course, put a dam at the sea, the water will not get there. It's just to illustrate to you what areas would become below sea level. And then to just not make you panic, you know, the Netherlands is, many areas are up to a couple meters below sea level already for a long period of time. But the Dutch government, they built these delta works, and they really ensure that the water cannot get into this slab. The dike would break, of course, then big areas will be flooded immediately because they are below sea level. So below sea level is not a drama, but you need protection to avoid water to get there. Of course, you will get problems with flooding from monsoon or heavy rain, because the water cannot naturally run away anymore because it's below the sea level. So you will have to pump it or have irrigation, which of course Bangkok already has, and I think they have improved over the years. So we go, I think this is 2,300, 2,400. I mean, we are I'm not here anymore. 2,500, but you see, if nothing happened, if nothing is done, and the situation would be the same, also with the climate change, and yeah, at some point, Bangkok can still be there, but it will become this elevated above the ground city, you know, where maybe the ground levels are not used anymore, but that's just futuristic movies. So the question to you, I answer to you is it sinking when it's happening? It already started. Yeah, I think it's in the late 60s. I think it already started. And of course, it's related to more and more people coming to live in the Bangkok area, industry, and groundwater is changing there. It's the same in Europe in the past. It will change, you know, when you have more people, you have more industry. Yeah, it's always to find a way, a balance between ensuring that the groundwater level is not exceeding certain limits. In Europe nowadays, the surface water is much cleaner, so we don't have to pump groundwater because we can use the river water, which still is filtrated. So there's different options, you know. So there is nothing. I think this was 2,500. Sorry. Okay, then quickly, and then I'm almost finishing. I want to show you the impact, but don't worry, it's just horizontally of this earthquake. And actually, why I want to show is that nowadays, you see there's all the arrows you see. This is co-seismic, the change in position due to the 7-point earthquake in Myanmar earlier this year. But just to show you now how many stations in Thailand, because the data will be processed actually using both Leo was data from RTSD, Department of Land, and also other groups. Actually, now Thailand has a very nice system that all the data is now collected at the data center of RTSD from all the stations operational in Thailand. And then you can use them also for research. So, nothing to worry about. The most motion you had was only 3.5 centimeters in the northwest of Thailand, and the Bangkok area moved 3 millimeters. But it moved 3 millimeters all of Bangkok, so there's nothing to worry about. Of course, you have seen some other problems related to the earthquake, but that means the motion during the earthquake, the land motion. And just to say, those co-seismic displacements, they pose no danger to Thailand. Of course, if they would have vertical motions, then we would have to also include them into our budget for the relative sea level rise change. But in this case, this earthquake, and actually just to, I talked to our geophysicist colleagues, I think this was also the worst scenario for ground motions in Bangkok you normally have, because if they would be ruptured more to the south, the effect would not be bigger than you had today. So you already had the worst situation of tremors affecting Bangkok, you know. So so for that way, the buildings that didn't damage were strong. They should not have to worry because you cannot get much more amplitude of the ground motion. I will also show you that in the next slide. And this is just a zoom in. But you see how many stations now Thailand has, which are used for mapping purposes, but can also be used for scientific purposes. Okay, now just to show you the different stations, I mentioned to actually, there's the same stations I talked to you about before. We are monitoring for many, many years for the vertical land motion. This is the one at the Naval Dockyard. I think this is the one at RTSD Survey School. Just thing I want to mention to you, they all are on different heights. The pier is almost at the sea level, a few meters above it. RTSD is on the top of the building. The building, strong building, but that's already, I think, 10 meters. And the last one we make use of is the station at the IGS station at Chulalongkorn University, okay? That one is 100 meters above. The building is roughly 100 meters. Now, why I tell to you that is that because we also looked at the kinematic. That's also something you can get from the GPS. GPS Galileo, even you get a very nice kinematic change of position every 1 second, because we got data every 1 second. And I just want to illustrate to you that it's a bit beyond the topic of this, but we are quite pleased with the result, that there are different heights of the GPS stations or the antennas. And then if we look at the kinematic motion, so this is minutes after the earthquake start. I think when the earthquake started, it needs to travel about 4 minutes, the seismic ground waves, before they reach Bangkok. And then you see clearly the response of the ground, you know. So this is latitude, north-south, longitude, east-west. And actually the vertical is mostly noise, okay? The vertical is not, in kinematic, is a very weak solution. So it's not related to the earthquake, so don't. But you do see very clearly the vibrations, the land vibration. The scale is centimeters. Now look, this is SPKN. This is the lowest station above sea level. Now if we go to RTSD, which is on 10 meters, you see that the swinging actually becomes much more. And this also explains some of the things you have seen during the earthquake. If we go to the highest station, 100 meters above at Chulalongkorn University, you see that there even the building was going up and down. We have 1 second, I think, and the building was moving like 20 centimeters. I think many people saw. Some buildings start to get a bigger amplitude because it's a response. But actually this data is not related to this project, although you see also in the vertical here in the bottom, you can see actually the earthquake is actually lifting the building up 1-2 centimeters as the ground wave passes by. But you see afterwards that building is exactly at the same position. So this data, and you can see the aftershock also actually after 60 minutes, there was a 6.3. The higher the building, the more the swaying the response will be. And actually this data, we're going to publish it. I think can be useful as a real data case for the construction engineers, you know, because you have the building regulations, but now you have the real data measured, you know, which structural engineers can use. Of course, they put a safety factor on that. But actually, as I mentioned to you before, this is probably the worst trembling Bangkok can get. Because from Sumatra, you can also feel, but it's much less. The way from Myanmar, and I'm not the expert on the geophysics, but actually has to do a lot with a very thick sedimentation layer, which is also important for land subsidence. And when the seismic waves enter, actually in the north, when they enter on bedrock, you see very short vibrations, but not this bigger amplitude. But as they get into the Bangkok plain, the whole Bangkok plain, because it's such a thick layer with sand and water in between, becomes like this slushy, I will not say water, you know, but it starts to actually move by itself, you know. It starts to move more to the seismic wave interference. So anyway, this is very nice bit side effect. But we're using the same stations for our long-term vertical land motion and relative sea level rise, and yeah, to also measure this. So this one, okay, we will publish. Okay, so this brings me to the last slide. Some things to take away is actually that Mark will show you that at present the rate of absolute sea level rise, which we cannot deny because of the climate change in the Gulf of Thailand, is around 3 millimeters per year. But then at the same time we see that the GPS shows vertical land motion below this pillar depth, I assume 20 meters here, it can be 10 meters, which is 5 meters per year still, and it's already ongoing for at least 25 years. Then SAR, Milan will show you, INSAR, these other techniques, shows you that also that the rates actually, or Adapo will show you, we had up to 3 centimeters per year in some areas in the past. And it can change through the years, right? If the groundwater is not being pumped anymore, or there is more rain, or more, so that's it's not a constant value. So if you combine all that, you can see we are now able to put some more accurate numbers on the impact for Bangkok. And Bangkok is not too bad compared to, for example, Jakarta. Jakarta is 5 centimeters per year. They suffer a lot. So Bangkok is not doing too bad actually. But of course, for the long term, I think it would be good to try to have especially because it affects the human society along the coastal regions, to see if we can come up with, what if the government is being aware, or the policymakers, to do something about it. I think politics, I never intervene with that. That's every country does the politics as they want. We as a scientist, we just want to provide reliable scientific results, and then the policymakers can use them. Now, in the future, because we're still going to continue with this, because this is a long-term study in a different project, hopefully again with many of the same colleagues participating, that we can refine and we can see the more local impact. And to show you, actually, I'm going to show you a result from 2013. This was another project we did, GTTD Song. Back then we didn't have all these accurate estimates on the vertical land motion, but to show you what you can do with that is that you take the map, you take all the buildings there at GIS, and then you can enter the effect of sea level rise and land subsidence. And then what you see here is, I think green, the time scale, the color scale, I think green means low land subsidence, and red means high land subsidence. This is a test area, I think Samut Prakan area. And pink is actually areas which are below the sea level, but they are protected by natural or dikes or buildings. So with this, you can estimate in 5, 10. This is an old result, but we can redo it with the latest results, and also including groundwater extraction and pumping scenarios and more IPCC accurate results on the absolute sea level rise. Then you can really see in detail which areas will have an issue, and where, example, the red areas, you would have to put dikes. You don't have to put dikes immediately along the whole coastline, although if you can. But some areas you see it's not needed. Okay, so and then the very last one, and then I stop talking, is also I have shown you that at least at 4 locations we have our own data. We see that the land subsidence below 20 meters is up to 5 millimeter per year. And then for the future work, I think, and this earthquake already demonstrated that, we also want to use all the available data from Thailand, from the new stations which have been installed by departments or government agencies, and I think most of them started since 2019, so we have now 6 years, so that would be interesting to see at the vertical land motion at all those stations. Also further away from land, but we will focus, of course, for the coastal region. Okay. There is a small impact from this 9.2 earthquake, but I don't want to go into detail of that. But if you want to do the science perfect, yeah, you also take that one, although it was only 10 centimeter at most, the effect would be. So, and then, yeah, I think I try to show you or promote that we have more than one technique to measure relative sea level rise, so we can validate. So that's also good if you have discussions with anybody or policymakers, that you can show, yeah, we have 2 different techniques, and they both agree within 1 centimeter or 2 centimeter that in 50 years from now, this area will be 1 meter below sea, for example. Okay, so I will provide you the PDF, but with that, and I hope I didn't take too much extra time. Thanks for your attention, and hope to see you again in the future. So, thank you. And any questions, of course, you can ask.
So thank you, Wim. Are there any questions from the floor? So Dr. Amarin.
Thank you very much, Professor Wim. So I'm very excited about your research. So as someone that had no technical background on your topics, the subsidizing, let me add that. So the first is that how can we distinguish between the sinking of the road or building or our house is sinking, is collapsing? It's from the groundwater extraction or about the natural soil subsidence, or what about like the poor construction? How do we notice that? How can we know about this?
Yeah. Well, if I show you 2 cases, I think in Phuket there is rock. So there it's mostly because of the natural cycle related to tectonics, plate tectonics. In Bangkok, also that exists, but the scale is much smaller. Bangkok has a very thick sediment layer, I think up to more than 1,500 meters. You have the sand layer before you hit the bedrock. In this sand layer, you have different aquifers, layers with water, different depths. They also change a little bit where you stay in the greater Bangkok region. But all the land subsidence occurring in an area with a thick sediment is, well, unless you have a sinkhole and there's some water flushing away. You've seen the example of that, in Bangkok. But if you look at a longer period, stable period, this is always related to groundwater extraction. But the groundwater can already be extracted 10 years ago. Then you also have this effect that still the sand is compacting through the years as well. So if you are anywhere in the greater Bangkok region and you're not in Chonburi or Pattaya where you have bedrock, you can see the area there, then all the motion of your house is a result from changing in groundwater levels. And the response of that of the clay compacting when the groundwater is disappearing. Now, how much depends, of course, how deep the foundation of your home is. If your home is on pillar of 5 meters, then only what happened below the 5 meters is making. That's why you sometimes see the road. I think Dr. Anapa will show you, Femke showed you. You see the road is here and the bridge is here, and you see the road is down. This is because the upper layer is not. It's just laying on the sand. So everything what the upper 5, 10 meter is doing, because there's also water in there, is making the land go down. But just to answer you, in Bangkok, I think land subsidence is coming from groundwater extraction. There is no tectonic process active that can explain, there. So there is a small component from, they call it ground compacting, because you put a lot of buildings on the land, and they have a lot of weight. Okay, so they do have an effect, but that effect normally is just a temporary or a compression of the land, the sand below, and then it would stop. But what we see here over many more years, it can only be, although there is a small, but that's much smaller tectonic related to the groundwater changes, which can be natural as well. A well can fill up and more during to the rain, and the penetration to the earth, to the sand. So I hope that it's a long answer, but I think it's human-induced land subsidence is 99.9, or a local effect like a sinkhole, but that's very evident that that's local and related to the sand being flushed away, below, due to also water, but mostly rainwater or a leak in the water pipeline.
Thank you very much. So another question is about the INSAR technology. That's maybe you know or you don't know. That's in our country, in another province, not only in Bangkok, we still always use the water, the groundwater extraction. So many villages will do like that, not only in Bangkok but almost in many provinces. So for the INSAR technology, can we use this technology to observe in quickly that which province or which tambon or ampere or village that will subsidize?
Yeah. I think Milan and Dr. Arapo can answer that, but in detail. But yeah, you can measure anywhere with the INSAR. You can measure the subsidence. I just want to make a small remark with that, is that INSAR is only measuring relative subsidence. And it's a radar images, for example, 60 by 30 kilometer. If the whole area is going down 5 centimeter, that you will not see. But if one area is going down 3 centimeter and the other area is 2, then you can see the changes, Normally what we do is that we use GPS to make it absolute, because the GPS is an absolute measurement, and you can get INSAR or SAR results from the location where the GPS station is, and then you can combine. Actually, Milan probably will show you how to do that. Yes, you can do anywhere in Thailand. The INSAR results which will be presented today is actually showing the whole coastal region, not only the greater Bangkok, and you see different pockets also with land subsidence, and which all, of course, are related to groundwater or new development areas. Sometimes you have to lower the groundwater also. We did in Holland. If you put a city, and we had the swamp area, they had to lower the groundwater. That's even, they have to do, It's not because people are illegal pumping. Also, then you see the effect through the years that the sand on the surface is still slowly going down, But yes, you can use it. I think the data is free. Dr. Anapa Milan can explain you. I think the latest satellite from Europe, Sentinel, is providing the data is there, and you can choose basically any region in Thailand to do it. So, but he will have more details. But yes, you can do anywhere. You can see immediately where you have the subsidence relatively to area, because not all area are subsiding, So, okay. But good questions, so thank you.
Okay, so we would like to have some break, like 10 to 15 minutes. Thank you.